approach studying quarkonium production at the small transverse momentum. So this is fragmentation within a groomed jet. It's the same in-jet fragmentation that we had before, but instead of taking the whole jet and studying the fragmentation within the whole jet, we studied only after performing a grooming process on the jet. So I'm going to explain what the grooming procedures that we follow, particularly here the soft drop, the special case of soft drop, and then how does the how does the cross section factorizes in the soft collinear effective theory. I will perform the resummation and the evolution in the momentum space and impact parameter space, compare the two and see what we can learn, and then show how can we use this observable, which is within groomed jet hadronization, to probe TMD evolution. So the grooming process is the following. Well, you start with a jet. You have to have a jet, no matter what kind of jet. And it could be an anti-KT jet, but once you have the jet, you isolate the constituents and you perform a CA, Cambridge clustering algorithm, to the constituents of the jet only. So and every time you do a clustering step, you keep a record of the clustering process. The algorithm will first cluster the hadrons that are, or the particles that are close in angular separation, and we continue up to wide angle radiation. Then the declustering process starts. Now you have the record of with the order you cluster the particles, and you open the jet in the reverse order. In every step that you open the jet, you have a branching of two pseudo particles. Let's call them I and J, and you test this condition. If this condition fails, you drop the softer of the two branchings, and you repeat the same process. You open the pseudo particle J, and you test the process, and you test this condition. If this condition is true, then you stop, and the two branchings that you have is your groomed jet. Now, effectively, what that gives us is removes the soft wide-angle radiation, and you have only the energetic core of the jet, and that means that you're insensitive to boundary conditions and therefore non-global locks that there was a discussion in the previous talk. Also, if it's relevant to the experiment, it will mitigate the effects of underlying bend, which comes to be important in radiation close to the boundary. So how does the cross-section factorizes in the presence of groomed jets? You have a weighting function here and a jet function. This weighting function, in the case, if we consider a simple example, E plus E minus, will be the Born cross-sections times the Hart function from the matching of the soft collinear effective theory and the QCD, a soft function and a jet function for the recalling jet. And then you have the second jet function for your second jet. Now, we push everything else in here because, as I said before, the measurement only depends on the collinear radiation that is in the groomed jet. That's the only thing that we perform the measurement on. But the weighted function could depend on the collider, could depend on initial conditions, and could depend on any other Kazaa experimentals we'll put in. So what is the particular measurement that you will propose? What would be M that we propose here? You start with the particles that you have. You perform a grooming, a jet algorithm. Let's say that it's anti-KT because it's the favorite one. And then you have a jet or a hemisphere jet. You have a jet or a thrust axis. And traditionally, you will measure the transverse momentum of this identified hadron with respect to the jet axis. Now, instead, you perform a grooming algorithm. This will shift the jet axis into a different position, and you measure the transverse momentum of the identified hadron with respect to that new jet axis. And in addition, you measure the energy fraction of the identified hadron with respect to the energy of the groomed jet. So how does the cross-section factorizes now? Is the same thing as before. It's just that we change the notation to be consistent with what exists in the literature. So we have the TMD fragmented jet function or the TMD FJFs, Grooming in that case, we use the calligraphic letter G for the TMD FJFs, and it will depend on the hadron as well, not just the initiating part. And we will focus on the KT, which is the transverse momentum of the jet with respect to the hadron axis instead of the reverse, because it's easier to refactorize this term later. So this is the operator definition of the Groomed TMD FJF. It looks very similar with the standard TMD FJF. The only difference is that you have to impose soft-drop condition on your Hilbert states, the intermediate Hilbert states. And in the effective field theory, we focus on this kinematic constraint, which seems to be the most relevant one, especially if you're planning to study the small transverse momentum limit. Usually zika is taken 0.1, and that's the numerics that we're gonna do here. In this kinematic regime, then you have two relevant modes that will contribute to the measurement, the collinear soft modes and the collinear modes, with this scaling each one. And then we can refactorize the TMD FJF further to a soft function and a purely collinear term. The operator definitions for those, again, here we have the purely collinear term, which is the same as you have in any other TMD FJF, if either groom or ungroomed, because it's a collinear term and therefore insensitive to the grooming process. And then you have the soft function, which will depend on the grooming parameters, zcat, but it will not depend on the energy fraction, since this is parametrically less energetic than the collinear modes. As always, if I consider KT much larger than lambda QCD, I can refactorize the purely collinear term into something that is a matching coefficient. It's a Wilson matching coefficient. It's purely perturbative calculation and the collinear fragmentation functions. Now, of course, if you're measuring transverse momentum, you're going to run into rapidity divergences, and you need to regulate those appropriately. We use the rapidity regulator for the rapidity divergences, and similar rapidity divergences should be expected when you calculate the soft function. An easy test to do if you did the perturbative calculation correct, or at least part of it correct, is to sum the two anomalous dimensions that come with the rapidity normalization group from your purely collinear term and the soft function. If those two cancel, then you satisfy the normalization condition, since those two functions are the only function, the cross-section, that has to depend on rapidity divergences, and therefore their anomalous dimension has to cancel between the two. Now, Ignacio talked about the dependence of how to perform the rapidity evolution and the virtuality evolution, but here we choose just the traditional approach, where we first evolve in rapidity the soft function up to the collinear scale, and then evolve the product of the two from the soft scale up to the hard scale. And there's two ways you can do this evolution. You can do the momentum space evolution, which is take the Fourier transform of the RG, solve the RG in the Fourier space, take the inverse Fourier transform, and then fix the scales. If you do follow this process, then you get the following result here. Now, you never follow this procedure. And the reason you never follow this procedure is, for example, our next leading log, you end up with this gamma function in the numerator. This gamma function is 1 over minus omega s, and diverges in all relevant regions of KT. In order to get omega s given by this expression here, both for the groom and the ungroomed, is the collinear rapidity scale divided by the soft rapidity scale. The effective field theory is more appropriate when this logarithm here is large, when these scales here are widely separated. But in that region, that's where omega s close to 1, and that's why you don't usually follow this procedure if you're studying traditional TMDs. But for the Groom case, this is just a log of zeta. So it does not depend on kt at all, except of the alpha s. And therefore, if omega s for a particular value of zeta is a good choice, that means that it's away from 1, then you can probably use the momentum space resummation throughout until you hit the Landau pole. And we tested that indeed for zeta at 0.1, you can do that. Here's a comparison for the resummation momentum space against some Pythia simulations where we turn off the hadronization in order to compare against our hadronic results. This is for energy of the jets, 200 GeV. Q is 2 times the energy of the jet, so it's the invariant mass of the plus and minus. And zeta 0.1 for 0.6 for the energy fraction and 0.7 respectively. Where?
The next one. Simulation. Yeah, I was thinking about when pH, P perp, then you go back to 0.
No, so we cut it about 1 GeV. The reason is because, well, the perturbative result here is going to hit the Landau pole at some point, so it doesn't make any sense unless you use the corresponding Bmax in momentum space would be a PT mean. Now, Pythia, because this is purely patronic and it's a PT ordering algorithm, it drops sharp to 0 at 0.4. So it goes up, maybe a little bit creates a peak, and then sharps down to 0. It's around half GeV where that happens. But because we can't do momentum space resummation, doesn't mean that we have to. We can do the impact parameter space, and that is reversing the order of the last 2 parts of the process. Basically, fix the scale after you solve the RG in the impact parameter, and then take the Fourier transform numerically. So that will give you the following expression. This is an order expression here. I didn't write the next building block which we're working with. And the reason why I did that is to point out that here, this expression here is what we have for the rapidity anomalous dimension. Either perturbative terms or non-perturbative terms, this is the rapidity anomalous dimension. And the whole thing multiplies the log of zeta. So that will become important later on. So this is the rapidity anomalous dimension. It has to cancel against the collinear term. The collinear term does not depend on zeta. So the rapidity anomalous dimension does not depend either we do grooming or we don't do grooming. Usually we model the non-perturbative part by taking the perturbative rapidity anomalous dimension, taking B to B star. This is a convention for B star, and then we add an additional term, which has to vanish as we go to 0 because then you want to recover the perturbative result. We choose 4 models, or 2 models, 3 fits. We didn't have to do that for what we're doing here. We could just choose like 2 models and then make a grid in the various parameters, but we choose these particular 4 models for the numerics that we are following. So just to have in mind that for the numerics that we are following, this is the notation we use for these 4 situations. And first, I wanted to compare the momentum space with the impact parameter space. I claimed that I can do the resummation in momentum space. So if I can do that, then I should be able to compare it with the impact parameter space. And for regions where the model dependence comes in, then there is some difference. This particular model did not have that much difference with the momentum model that we use. But for the perturbative region, then we can see that basically they're on top of each other. So indeed, the momentum space and B-space resummation in the region where you don't have model dependence, they give you exactly the same results. And the same is true for the other 3 models that it was on the table before. So how can we explore the sensitivity of the anomalous dimension, of the rapidity anomalous dimension, to this logarithm in front of it, in order to get some additional information regarding the non-perturbative part that comes with the rapidity anomalous dimension? Well, one approach that we thought that might be interesting to study is to normalize the cross-section and then take the logarithmic derivative with z-cut. And we did that for the 4 models here. I cut the product 5 GeV because after that, basically, what you get is that all 4 models give you exactly the same result, which is what you expect, since here is where the perturbative cross-section kicks in. And for a region before starting, the z-cut dependence starts becoming important for the TMD function itself. We can find a region where is between lambda QCD and approximately here 3.5 GeV, where you can fit and become sensitive to the model that we use for the rapidity anomalous dimension. So summarize part 1, we use soft collinear effective field theory to study groomed jets and hadronization within groomed jets. We show that, actually, we argue that non-global effects are not important for Groom observables, and can be easily extended to other. Here we measure the transverse momentum of the hadron, but it can be extended for any other jet substructure you want. Particularly, we have the results for jet mass and generic angularities, although we didn't publish those because they were not in connection with that paper, with that project here. Can be easily extended between E plus, E minus, and EIC. The only difference is the weighting functions in front of the jet function, and those are not. Those can be fitted through different observables if you don't want to calculate them, but they can be calculated in perturbation theory. And we extended the study to heavy quarks, particularly B mesons, and we added, in that case, it turns out it's important to add threshold resummation, or logs of 1 minus x start becoming important. We show that in the perturbative regime, can be studied in the momentum space, not just the impact parameter space, and in the non-perturbative regime, it can give you a good discriminating power between various models for the non-perturbative part of the rapidity anomalous dimension. So now I switch to part 2, which is effective field theory approach to Quarkonium production. This is collaboration with Sean Fleming and Thomas Meehan, and I will have one slide review for what is NRQCD for PT larger than MQ or of the same size as MQ, and then some preliminary discussion on the effective field theory that we're working on in order to describe the low transverse momentum of Quarkonium. So this is NRQCD factorization. It's a very simple one. It says calculate the cross-section for producing Quarkonium is the sum of these products here. Calculate the cross-section to produce a QQ bar in a particular color, an angular momentum configuration, multiply with a number that depends only on this configuration, and you have the cross-section. You have to fit those because it's non-perturbative numbers, but then for each production, they have a particular scaling in the relative velocity of the heavy quark and anti-quark, and therefore you can truncate this sum up to particular accuracy that you care about. Usually we keep the first 4 for J psi and epsilon production. But if you want to try to study Quarkonium at low PT, then you run into trouble. Why do you run into trouble? Because NRQCD is valid for transverse momentum approximately MQ and above. If you go higher, way higher than MQ, then you might be able to use some fragmentation function approaches. If you go a little bit below, then maybe SFG, so gluon factorization might help you, but it's still under debate. But if you really go below at parametrically smaller transverse momentum, then NRQCD factorization breaks.
just a comment, even at the PT order of Q, NRQCD Factorization for hydrogen production has not been proved.
It has not been proved, yeah, but not even the concept of the factorization holds if you go really below.
That's true. And go worse.
Yeah, the expression itself, it just does not make any sense. So what was the previous attempts to study Quarkonium at low PT? There was a lot of approaches where they said, well, let's study color singlet model. In that case, then you can argue that there is no recoil between the QQ bar pair and gluon emitted from that. Or we can study the color evaporation model. So there was quite a few studies using these approaches. The problem with those is that they have other things that they get wrong when it comes to Quarkonium production, such as the polarization. For example, the color evaporation model does not predict it. Color singlet model fails to predict the data at large and moderate values of PT. So it's hard to believe that this is the approach we have to follow in order to describe the low PT region. Then there is a CGC methods where there is some small x, but they don't resum PT divided by n. And if you're studying upsilon, for example, then these corrections become important, especially if you're in the TMD region. So there, if you can argue that these logarithms are not important, or this expression, if this ratio is not large enough, but you have to sum small x, then maybe CGC works, but not for TMDs. Then there was, in 2012, an attempt using NRQCD, including some evolution. So what the authors did here was take NRQCD, the way it is, take the small PT limit. If we do that, we're going to recover some logarithms, and those should be the ones that we're going to resum. So just by reading the expression for the logarithms and the coefficient in front of the logarithms, they could figure out what the exponential factor should be in order to resum those logarithms. The only problem is that they assume that the factorization of NRQCD holds down to small PT. And that's what I'm going to argue here, is that NRQCD factorization does not indeed hold at smaller values of PT. So to start, what is the effective field theory that we're trying to construct here is based on SCT and NRQCD. It's not really just the sum of the Lagrangians. It's much more complicated, but schematically, let's say that is that. There is the collinear modes that they always exist when we study PT. Resummation, and that is PT divided by Q. And then there is two soft modes that are relevant to me. There is, I will call that the NRQCD soft, and that scales as MQV. And then there is the SCT soft, which scales as PT. So then the question is, what is the hierarchy between these two scales? And what does that mean for the factorization theorem? There's also the heavy quarks and the ultrasoft modes, but they're not going to play an important role for what I'm saying here. So you start by constructing the operators that are going to appear in the effective field theory, and then you match the QCD operators. That's, for example, the QCD operator, and the product of these two will be the operator of the effective field theory that I'm concerning. And then you perform a matching process, you get the Wilson matching coefficients. And after some standard SCT, BPL sphere definition techniques, you can write down a factorization theorem like that. Well, that's a huge step, but I don't really have the time within 5 minutes to prove that this factorization within the effective theory in this is true. But I'm going to try to say what each individual component of this factorization theorem is. Well, the hard function is the easy part. It's just the Wilson matching coefficients. You have a matrix element and the conjugate, and that will be bring a C and a C bar, and that will be the hard function.
Can I just have a quick comment?
Yes.
You pull this factorization formula for hydrogen plus.
Yes. Yes.
So stop, and I believe once you push your kinematic to low PT region, then the initial state, you didn't deal with the initial state. Initial state interaction from global, initial state interaction with PT to global region. Global region is the region sensitive to KT.
Yes.
So it's sensitive to some of the final state.
Yes.
So now you introduce the hadronic quantity of collinear produced with the low PT.
Yes.
So you sure that factorization is true? Or
No.
You can prove that.
No, no, no. Of course not. But if you really want to try to avoid the Glaubers, because the Glaubers are indeed there, and you really need to think if they cancel eventually, and I cannot say that they cancel, but if you...
At high PTBG, you could prove those factors.
At high PT, yeah, but here, where I'm concerning, I'm not sure if I can do that. And if I want to avoid the discussion about Glaubers, which I do, I will go to E plus E minus, where basically the hard function is going to be exactly the same, but now instead of having PDFs, I have fragmentation functions.
The E plus minus is more the problem.
Exactly.
But you're trying to find a formula for the hadron case.
Yeah. But it still has the same, it still is Quarkonium production or Quarkonium decay in that case. And you still have to find a way to study TMD effects. And NRQCD factorization will break in that case too. And I don't want to create an effective field theory that I'm going to study one process. I want to extend it to EIC, I want to extend it to CDs, I want to extend it to hadron colliders if Glaubers are allowed, and E plus E minus. But these two cases are kinematically the easiest one if you exclude the Glauber in case of the hadron-hadron. So we discussed about the hard function. The beam functions, or the purely collinear in case you're considering fragmentation, is simply the matching coefficient times the collinear corresponding, which in that case, if this is a beam function, then we have the collinear PDFs, and we have a matching coefficient that can be calculated in perturbation theory. On top of that, you could have an additional model. Note that if you do include an additional model, this is a purely collinear term. It does not involve any soft radiation. So this is not the standard F, we call the TMD PDFs, where you absorb the soft square root of the soft function inside the collinear matrix elements. And then at the end, we have something that looks like a soft function, but it's much more trickier because it involves this O2 operator here from the Quarkonium production. And what we usually try to do is push this operator outside the matrix element and create a new matrix element. But there is no way you can argue that this object factorizes here, because there is a crosstalk between the Wilson lines that came from the two protons and the Quarkonium operator, because this is soft gluons, and the soft gluons in the NRQCD Lagrangian talk with the heavy quarks. So this is the best you can do. You can stop here and say, instead of a soft function, I'm going to have a shape function. And the shape function includes the production of a Quarkonium through these operators here. First test you can do if this factorization theorem holds is to go to next Ling order. Unfortunately, the factorization theorem does not hold even if you don't include Glaubers. What happens is that you find that for the S-wave, the octet case, there is an additional IR divergence that does not cancel. And that this additional IR divergence comes from the hard function, actually. And it's only particular for the octet. So this divergence is 1 over epsilon and multiplies a delta of 8n. So it really has to do with the octet case, at least for the S-waves. So what we were missing, it was that we started with a set of operators that it was the wrong set of operators. And they were missing the gauge link between the heavy quark and the heavy anti-quark. The Wilson line that we have here, so the Wilson line, not Wilson line. The Wilson line that needs to be included here is this particular here, is along the time-like direction, and involves the soft gluons. So if we do this transformation here for the heavy quark and anti-quark, If I looked at the singlet case, what will happen is, since because K here is just delta AB, we'll contract the two Wilson lines that comes from the heavy quark and antiquark, and it will give me back exactly the same operator. So no change. Good, because already I knew that at least at one loop, the factorization theorem holds here. But if I look at the octet case, this involves a TAB here, and then when I contract the Wilson lines, then it gives me a Wilson line in the adjoint representation, multiplying the old operator. As a result, this will bring here not only these two Wilson lines that we have, but an additional Wilson line that is not along the collinear direction anymore. The light cone direction is along the time-like direction, and knows about the Quarkonium. So it didn't come as a surprise that a Wilson line needs to be there. There was a work in 2005, I believe, that showed that indeed at two loops, you will need the Wilson line even at the large PT. And more recently, Ira, Prashant, and Ian Stewart published a paper that they say exactly this soft Wilson line that we introduced in the operator definition needs to be included in the Lagrangian exactly the same way as we included it here in order to make the Lagrangian of NRQCD soft gauge invariant. How did we motivate the existence of these Wilson lines in the operators? We started with QCD for particular matrix elements. We take the non-relativistic limit and we try to see what are the operators that we're getting. So if I don't include any gluons contracted to the heavy quark antiquark and take the non-relativistic limit, the only thing I would get is back is Schrodinger fields. Then I include the first gluon, take the non-relativistic limit. Then what happens is that I have a soft gluon here interacting with a potential heavy quark. That will push this operator to be a field that does not belong to the effective field theory and needs to be integrated out. During that process, I get an operator that looks like that, and the expression that I get in the non-relativistic limit involves the soft gluons, the zeroth component of the soft gluons divided by Q10. I repeat it for two gluons, and I get this expression, and I need to add the permutations. If I repeat that, it's very easy actually to repeat infinite number of gluons, and the expression you get is exactly that, which is the Fourier conjugate of the Wilson line that I showed in the coordinate space before. And that was done only for one of the heavy quarks. If I go to the anti-quark, there's another U that needs to be contracted to that guy. So basically that is what I wanted to talk about the effective field theory, but there is still a few questions that need to be answered. This soft Wilson line, is it a V-soft or a lambda soft? So this is NRQCD soft or is it SCT soft? Then what are the different hierarchy between the two soft modes? Because I talk about two soft modes, but they could be different in general. Can we do a perturbative calculation to check the factorization theorem? And how does that relate to what we already knew about NRQCD in the soft limit? And regarding the first question, I would say either there is no hierarchy, so there is no two soft modes, there's only really one soft mode, or there is hierarchy, and then push me to question number 2. So I thought that these 3 hierarchies are interesting, although in principle you can have many others. And I'll start with that one, where the PT is much larger than MQ. Then in that case, I have 2 soft modes, 2 distinct soft modes. Then the soft gluons, they will split into the NCT and the NRQCD soft, which means that this Wilson line would just be a product of these 2 terms here. As a result, the shape function now will be split into a soft function, still depending on Quarkonium, and the traditional LDMs that we had before. So this is the region where we will be able to reconstruct the soft limit of NRQCD. In region 2, which is more phenomenologically interesting, there is not really we can do. It's just what it is. It's like the 2 soft modes are 1 and there is no further factorization, not obvious at least. And then there's the region 3, which is kind of, if you're curious, then you can ask what happens if MQV is much larger than lambda QCD. Usually it's about 1.5 GeV. I wouldn't think that this is much larger than lambda QCD, but if you take it to be much larger than lambda QCD, then you can match the soft mode into a matching coefficient, and a new set of LDM is different from what we are feeding all this time on NRQCD. Check about the how can we perform a check. Then, as I said before, the most straightforward way is to check that the anomalous dimension, the perturbative results for the anomalous dimension cancel, and indeed for the virtuality they do cancel this way, and for the rapidity this way. And we perform this calculation. Then this is the connection with, we made the connection with this paper that I mentioned earlier, that indeed if we take our factorization theorem, we take this hierarchy here, perform the power counting, we recover the results from this paper, which they basically took the soft limit of NRQCD.
The second region, you see X nuance, know the whole recovery result, right?
Yes, yeah. So this is the conclusion for the second part of my talk.